discussed last time, we consider an interface between two transparent media with different refractivity. So that allows us to consider part of, if we have some incident ray of light originated from some object, reflected or emitted. So there obviously will be some split of energy carried by this ray. So part will be reflected on this interface, part will be refracted, so it will penetrate into the second medium and travel already in this new environment. So due to refraction, we can similarly to reflection use this phenomena to create some images of real objects. So optical images, considering these optical systems. Initially, we considered spherical mirrors, like flat and spherical mirrors, and now we switch to lenses. So initially, we considered just interface between, let's say, air and glass. Glass is the most common material which is used to produce lenses. And for this given interface, we derive the equation of refraction. So let's say equation of building images via refraction. So this is the equation which we derived at the end of previous discussion. And here we see N1 is refractive index of the first medium, then P distance from the object to the interface between two mediums, N2 refractive index of the second medium, and Q in the denominator is the distance from the interface to the image. Again, it may be either real or imaginary, so depending on where it's located and how refracted rays are intercepted, we will deal either with real and or imaginary image of the object. And in the right side, we have N1 minus N2 minus N1 and divided by radius. So radius defines the geometric features of the interface. To be more specific, it defines the curvature of this interface. We considered one example with a flat interface. So then curvature, like radius of the curvature, approaches to infinity. But this is one of the extreme cases. Usually these curvatures are present and they are described by some given number defining the radius of this curvature. So, as you may understand, so far in this equation, as we derived, it's applicable only in the case when we have a single interface between, let's say, air and glass. That is not what is practically used, because you may see in different optical systems, we have actually lenses. Lenses, they represent, by definition, a combination of two interfaces. What is there going on? So there are two interfaces. And obviously both of them will contribute towards the image formation. So in order to terminate, we need to analyze image formation by first curvature, consider image of the first curvature as an object for the second curvature, and then we will get final image created by a classical lens. In order to make it simpler, we will consider so-called thin lenses. So what thin lens means? That the thickness of the lens is smaller then the distance from the object to the lens, or distance from the lens to the image. We consider that this thickness of the lens is considerably smaller than distances which we operate with respect to the position of the lens, object, and image. So in that case, things are getting a bit more simplified, and we can get analytical solutions. So let us check this slide. So let's look at this left side image. So here is kind of exaggerated example. The thickness is well defined, so it's not negligible in comparison to distances. But later we will consider this extreme case when thickness becomes much smaller. So we have two surfaces, or better say interfaces. If we consider air, so N1 is equal to unity, so that's air. This is, let's say, glass with a refractive index N. So what happens first? There is our object. Then rays from object hit this first interface. And as we already know from previous discussion, this interface will create some image. So that's particularly, this is the image of the object in this given case. So who will tell me, is this real or imaginary image? Imaginary image, because we do not have over like cross of the refracted rays, so they do not cross here. That's why we need to extrapolate them and see the point of conversion. And image is located on the same side as the object. Yes?
Is it a blue line coming from the object is 90, like 90 degree to the object?
So this
Yeah.
blue line, so it is, depends how you define it, but this blue line is, it's convenient to define position, like orientation of rays with respect to principal optical axis.
And they're parallel.
Yeah, this is parallel. So this goes perpendicular to the surface of the interface. So now, as opposite to previous case, we have one more curvature, like interface. And in order to get the image of the whole system, which consists of two interfaces, means image created by a real lens, actually, we need to do several steps. So it's like multi-step process. First of all, we find the image created of this image of this object created by first curvature, this one, and then we consider this image as a kind of intermediate object for the second interface. Then we build image of this intermediate object and eventually get an image which is formed of this object, for real object O, which is formed by this lens. So let us do some calculations here. Come back. Whiteboard. So this is our equation for the interface between two optically transparent that was not for one-side lens, that was for interface between air and glass. And that's it. So we didn't consider the other side. So we considered just interface between two mediums. We didn't specify that the second media is somewhere ended. So it's kind of infinite air, infinite glass. And there is one interface. So this is the equation for this specific case. So that's why when we deal with real lens, we have sharply defined edges from both sides. We need to apply this twice, but specifically remember which medium is first, which medium is second, because they will change, so you may understand. So if we consider first interface, then first medium is air, second is glass. If we consider second interface, then first medium will be glass and second is air. So these all factors should be taken into account. So we consider surface number one. N1, if we consider in the scope of this equation on the top, so N1 will be equal to unity because that is air, and N2 will be equal to N. That's refractive index of glass. Then we can write for this specific case that 1 over P1, this is distance from the object, real object, to the air glass interface, this first interface, S1, then N over Q1. Q1 is the distance from the first interface to the image of the real object created by first interface. And this will be N minus unity divided by R1. So the R1 is the radius which defines curvature of the first interface. Keep in mind that curvatures can be either the same for first and second interface or they can be different. So that depends on the lens. There are different lenses. So this is the first equation which is important for us. Now let us consider second interface. So it will be glass air. In this case, N1 will be equal to N, and N2 will be equal to unity. So we can write that N divided by P2. So P2 in this case will be the distance of the image created by first interface to the second interface. So we will show this on the slide to make it more clear. So then plus 1 over Q2. So this will be distance of the object. This will be distance of the image created by the second interface already. So the final image which we are interested in, and this distance will be from this image to the second interface. And that will be equal to 1 minus N over R2. Yes, we consider two surfaces now. So we have two equations for both surfaces, and keep in mind that we consider kind of intermediate object for the second interface as an image of the first interface. Okay, so now we have these two equations, and let us come back to the slide. So this is P1 in the first equation, this is P2. So how we can represent P2 in terms of P1? So we have this P1 not in terms of P1, but in terms of Q1. So P2 is equal to minus Q1 plus T. So why minus? Because by magnitude Q1 is negative. Because we remember that if image is located in the same side as the object and its imaginary image, then this distance Q1 will be negative. So in order to get the absolute value, the magnitude, we need to take minus Q1. So minus and minus will compensate each other. So we will get just magnitude of this distance, not specifying it's positive or negative. And then we need to add thickness of the lens to Q1, and this will give us the P2, because P2 should be the distance from the image of the first interface to the second interface. So is it clear from the image? Let us write it down. It's right here. So we can write that P2 is equal to minus Q1 plus T. T is the thickness of the lens, or distance between two interfaces. Now we consider that T is small. So we consider a thin lens. So distance between interfaces is much smaller in comparison to these distances P1, Q1, P2, Q2. So taking this into account, we can write that P2 is closely equal to minus Q1. So now we can substitute this expression for P2 in our second equation. So that will be minus n over Q1 plus 1 over Q2, and that will be equal to 1 minus n over r. And here will be r2, the radius of the curvature, the second interface. So now what we do, we have first equation, let's mark it as 1 star. Then we have second equation, like 2 stars. So this is equation for first interface. This is equation for the second interface. Now if we add these equations together, we get the following. So it will be 1 over P1 plus 1 over Q2, that is equal to n minus unity times 1 over R1 minus 1 over R2. we can proceed even further because now, since t is small, we do not distinguish between first and second, like between distances to first and second interfaces, since first and second interfaces are located very close to each other. So in this case, we can just write, we can skip of these indexes because there is not a big difference between P1 and P2, Q1 and Q2, because T is small. So that's why we can eventually write 1 over P plus 1 over Q, and that will be equal to n minus unity 1 over R1 minus 1 over R2. So what we have here, actually we have an equation for image formation by a thin length. So this P1, which we denote as P, that is distance, actually, so of an object to the center of the lens, because here we don't consider first interface or second interface, they are close. We measure all distances now with to the center of the lens. So P is the distance of an object to the center of the lens. Q, it's a distance from the image created by the lens by two curvatures to the center of the lens. And here we have refractive index, so unity we have because it's air, so n is refractive index of the material of the lens. It can be glass, it can be quartz, it can be even some materials which we would never consider as materials for lenses, because everything defines where we operate in which spectral range. So, for instance, if we have some night vision instruments which operate in the long wavelength region, like IR spectral region, with about 10 micrometers wavelength. In that case, we cannot use glass because of several reasons. First of all, glass absorbs quite a lot in this spectral range through IR spectral range. It's transparent for visible range, but absorbs quite a lot in the IR spectral range. Second, we don't want to get any visible light as background noise to our detector. So we want to get only that spectral range we're interested in, and that is spectral range next to 10 micrometers in order to see some warm objects and convert them into some electrical signal and see on the monitor. So that's why for such systems, lenses are used from, for instance, cadmium telluride. Cadmium telluride is a semiconductor material with band gap of 1.5 electron volts. And it is, if you look at this like crystal, it's just dark brown. It doesn't let any visible light to go through. So if you have some lens made of this material, it's just opaque. You cannot see anything from that. But it's opaque only for visible spectral range. For infrared spectral range, it's actually transparent and much possesses much higher transparency than regular glass. So that's why, first of all, it let efficiently IR spectral range through it. However, it completely blocks the visible light, so it will not interfere with our useful signal and create some unnecessary background. However, it doesn't matter which wavelength region you are operating in, doesn't matter which materials you are using for making lenses, this equation is working for the image which will be formed by these lenses. The only information you need to know the refractive index, curvatures of the first and second surfaces, and also make sure that in given spectral range where you're going to apply these lenses, this material will be transparent. Because as you remember from beginning of previous discussion, we highlighted that we need to have interface between two transparent medium, and materials of different materials are transparent in different spectral ranges. So this should be taken into account. So now what we can also write, this is another equation which introduces focal distance of a lens, 1 over f, which is focal distance. How we get to this focal distance? Again, if we consider rays which are traveling towards the lens exclusively parallel to the principal optical axis, then they all will converge in one point. And that point is called focus of the lens, and distance from the lens to this point is focal distance. So now if we consider P approaching infinity, so that's the case when all rays will travel parallel to the optical axis, prime optical axis, then 1 over q will be equal to n minus 1 times 1 over r1 minus 1 over r2. And this is actually the way how we determine the focal distance. So 1 over f will be equal to n minus unity times 1 over r1 minus 1 over r2. So this equation is so-called lens maker's equation. Because if you decide to make optical systems and lenses, so this is the equation you will work most of the time. So why it's so important? Because, for instance, any suggestions why this equation is not called lens maker's equation, but this one?
Because we make only one side of the lens and the blindness.
No, but in both cases we have two sides of the lens. You see, we have R1 and R2. In both cases we have both. And when we make complex optical systems, like if you consider some photo camera objective, so then in order to compensate for different optical disturbances and deviations, you build a combination of different lenses. So they are stick together literally with some special glue, optical glue, and then they become quite complicated optical systems. But when you make a single lens, then you always deal with two surfaces. It can be different, can be one with curvature, another can be flat, or different curvature, whatever. But when you make a lens, you automatically have to deal with two lenses, two interfaces. So, any suggestions why? Actually, the right sides are the same. So the difference obviously is here.
Maybe for making lenses, there's no need to know the distance between the object and the
Exactly.
image.
So
we
this
need only focus.
This can be anything. Distance to object and distance to image can vary from 0 to infinity. The two important parameters: focal length, because focal length is, if you look at this right side of the equation, so focal length can be defined as a unique parameter of a given length. Every length will have this focal distance, which is defined by properties of the material it's made of and curvatures of two interfaces. So if you know which focal length your focal distance your lens should possess, then you know, for instance, you pick up some material and then you automatically know which curvatures you need to provide to the interface. So that's why these two equations are quite important in the formation of image by means of the lens, and specifically the second one for actually making lenses with given properties. Also, so now finally we can write down the general equation. So it will be 1 over p plus 1 over q, and that is equal to 1 over f. As you remember, we had similar equation for mirrors, so they share this concepts, but in the case of mirrors, what was the focal? In case of a spherical mirror, what was the focal distance? Of radius, yes. In this case, you see that this is a bit more complicated in comparison to mirrors. So obviously, there is also some magnification of a lens. So we can write here that m is equal to h prime over h, again similar to what we did with mirrors, height of the image divided by height of the object, that will be minus q over p.
How they are sharing okay with something like that.
I mean, they are sharing the general view, so of the equation, shape equation, but the fact that here this f, focal distance, is different for mirrors and for lenses. So focal distance for mirrors is defined as radius divided by 2, so 1/2 of the radius, and focal distance, like actually 1 over f, for lens is defined by more parameters. In lenses, in mirrors, we do not care about refractive index because rays are traveling in one medium. It's always in air. It just reflected from the interface and was traveling in air before it hits the mirror, travels in air after it hits the mirror. So we don't care about refractive index. So first. Second, we have only one curvature for mirror. That's why we deal only with one radius of the spherical mirror. So eventually, we have focal distance as a function of a single parameter, which is the radius of the mirror. So actually, focal distance is twice smaller than the radius of the curvature of this spherical mirror. In case of a lens, we need to take into account more parameters. First of all, refractive index, because as rays are traveling, they go from one medium to another and then come back again to the first medium. So we need to know the refractive index of the first medium and the second. Here it's unity because we assume that lens is located in air, which is most common case. N is refractive index of the glass. And also we have now two surfaces, interfaces with different curvatures. So these factors should be also taken into account. So we have the same general equation for mirrors and lenses, but where P and Q are distance from the object to the mirror or lens, and Q from the image to the mirror or lens, but F is defined in different ways.
We equated last two formulas. Yeah. Get it.
Yes, so so this is the first equation gives us this is the equation for the image formed by a lens. This. So then we consider that our object is located very far, and distance from the image will be given in this case because 1 over p will tend to 0. So we get rid of it. So we know that when rays are traveling parallel to the principal optical axis, they will go through the lens and converge in one point. And that is called focus of the lens. And distance from the lens to this point, which is this case, the distance from the lens to the image, when all rays are traveling parallel to the optical prime optical axis, will be our focal distance. So we can introduce now focal distance, like 1 over focal distance, equal to this equation, which is this part. And now we, instead of this part, because they are the same, the right sides of this equation, we just substitute 1 over f. And that's how we get this equation.
Why we assume that p becomes 0? Because it like 1 over p becomes 0. But in the general equation, we don't write that. Like,
Well, in general equation, that's the reason why it's general, because then p may possess any value. P, you may go from infinity to actually 0. You can place your object right in front of the lens.
But will it still be equal to the 1 over 4? Oh, yeah, of course.
No, so this 1 over focal distance will be a property of the lens. It will not depend, it's constant, it will not depend on anything else than the properties of the lens. And as you see, this expression for focal distance is located in the right side of the equation. It has nothing to do with p. So that's why we wrote here 1 over focal distance is equal to 1 over p plus 1 over q. If p is infinity, then this will be 0, and 1 over q will be equal to 1 over f. That means q is equal to f. So it means that our image of this infinitely large, infinitely far located object will be converged in one point at the distance equal to focal distance of the mirror, of the lens. So, if we consider some optical instruments which are using mirrors and lenses and doing actually the same job, do you have any example? For instance, have you seen microscopes which are working based on refraction and reflection?
I think that use it in the underwater like ships. They have things that use to see the
Periscope.
let's base it on the reflection.
Well, no. So it has embedded systems for reflection, obviously, because you need to like make some curvature for light to pass. But that's only to change the trajectory, because there you have lens like as an objective, and ocular as another lens where you observe already with the eye. Actually, you have some prisms with 45 degrees mirrors just to um, send your rays in direction you want. But those mirrors are flat. They are not changing the image. So they only reflect what hits them. So in order to go at right angle. So if you have a mirror located at 45 degrees, then you just get reflection down. And then you do it once more, and then you can easily observe the object. So I'm talking about systems where mirrors are not flat, but uh, uh, so let's say lenses they by definition need to be curved, so they cannot flat. Lens is just window glass, so it doesn't disturb the image. It just shows just let rays to go through without any disturbance. But mirrors, if we're talking about mirrors, we want to have some spherical mirrors or parabolic mirrors, which actually form image by themselves, so not just reflect light. So the one classical example of optical instruments, which both can be based on purely lenses or purely mirrors, are telescopes. So there are so-called refractors and reflectors. So refractors, they were originally proposed, if I'm not mistaken, by Galileo. He used two lenses to see the satellites of the Jupiter. And later, Newton came with idea for using mirror, like spherical mirror, for so-called reflective telescope. So in this case, there are no lenses. There is only one uh, mirror which reflects light. Then you place a 45 degrees mirror to change the direction of light to the ocular, and then you can observe it with your eye, the image. So in that case, you don't use a lens objective, you use mirror objective. So there are two designs for telescopes. If we consider amateur telescopes, like small size, most of them are made with lenses. But all professional huge telescopes with large diameters, then all of them based on actually mirrors. And if we consider the latest modern telescope, space telescope, James Webb, which was sent to its location in space between Earth and Sun last year, it's also a mirror, like reflective telescope. So it's specifically designed to operate in infrared spectral range, near infrared spectral range. So instead of depositing um, aluminum or silver on its mirrors, which consist of many segments, they were using deposition of gold layers in order to get maximum reflection in this near IR spectral region and get maximum of collected light. So why this main mirror is segmented? Because you cannot, so its the diameter is something like 7 meters, so you cannot fit such a mirror as one piece in any rocket. So it should be folded many times and then unfolded already when it's delivered to its permanent location. So that was quite a challenging task to do because you need to align each segment quite precisely so they work together as a single mirror. But eventually it worked out, and now it has capabilities to look into the furthest part of the visible universe. So, with this, we finish our discussion of uh, geometric optics. And next time, from next week, we will start our discussion of wave optics, in particular, such phenomena as interference, when we have interaction of two waves with the same wavelengths, but certain phase shift between them. Thank you very much for your attention and have a good day.